Welcome back. This is an Aleks training video on identifying carbon hybridization in simple organic molecules. When S subshells and P subshells are not completely full, they will reconfigure their electrons to maximize the energy that they have. And what they do is end up not staying in their rooms. In fact, their rooms actually kind of morph into different kind of rooms. So rather than an S, that is a specific place where electrons live, and P, where there's specific place where electrons live, in reality it's a little more complicated, very much more mathematical than that. So there's a hybridization, and a hybridization is based upon how many what the type of bond it is. Is it a single bond, a double bond, a triple bond? And then what type of overlap bonds, sigma bonds, like a sigma, simple overlap bond. And then the pi bonds, remember, are more three-dimensional bonds, kind of sticking up and down out of the plane of the molecule and sharing electrons in kind of over the heads of the other atoms. So they're asking here for tag all the sp2 hybridized atoms in this molecule. Okay, so which ones are sp2? Well, let's remind ourselves these shapes. Okay, if you were to have something like this, a carbon with 4 double bonds, okay, that is 1s and 3p, and it's going to be an sp3 hybridization. Okay, and so there'll be 4 sigma bonds and no pi bonds. If you were to have a double bond, okay, and I see some double bonds in this one, what's actually going to happen is you are going to have 1s and 2p, and it's going to be an sp2 hybridization. There's going to be 3 sigma bonds, 1, 2, 3, and then 1 pi bond there. Okay, so the other possibility would be a triple bond, where you're going to have a triple bond coming out of the carbon. In this case, I've got 2 electron groups, and that's an sp orbital. It's got 2 sigma bonds and 2 pi bonds. What else? Possibilities. What if I had 2 sets of double bonds? Okay, that would also be sp, because I've got 2 electron groups, 1, 2. 2 electron groups, 1, 2. So that's sps. sp2, I've got 3 electrons group. Okay, an s and then 2 p's. Here's an s and here's 2 p's. That's an sp2. And here's sp3. Here's an s and 3 p's. Okay, that's how I remembered it. So in sp, here's my s, here's my p. Okay, so it must be straight. Here's my s, here's my p. So that must be a straight angle, 180 degrees. Here's my s and here's my 2 p's. So this must be sp2. So it's at 120 degrees from each other. And then here's my s and here's my 3 p's, and that must be a tetrahedral, which is 109.5 degrees three-dimensional from each other. Okay, if you were to ever have something like this, kind of like the first one, but I have a lone pair. Well, that lone pair is still a group. It's exactly like this group, okay? Just because there's not a bond there doesn't mean there's not an electron group there. So this, and this would be the same, okay? Which means that it's an sp3. And if for whatever reason I was stuck, let's say I had a cation, I was stuck with only 3 bonds there, where there was no double bond, no lone pair and no bond. There's only 3 things coming out of the carbon. Well, that's 3 things. I've got 3 electron groups, so that's an sp2. Okay, I've got the s and the 2 p's. All right, so where's my sp2s? Okay, sp2, I've got 3 things attached to the carbon. it's sharing a double bond here and 2 single bonds, or what's the other sp2? That was the only sp. Oh, here it is, where you only have 3 things coming out of it. Well, do you see any atoms? Now, the hydrogens won't count because they can only hold hands with 1. So it's obviously the carbons are talking about. Is there anything that's holding hands with 3 things? Okay. Well, yeah, there is. This one's holding hands with 3 things. Okay. Hydrogen, hydrogen, and a double bond carbon. So that one is an sp2 hybridized carbon. Is there another thing holding with 3 things? What about this guy? No, that's 1, 2, 3, 4. That's an sp3. What about this guy? 1, 2, and a double bond, 3. Yes, that's an sp2. So these 2 carbons are my sp2 hybridized.